For this lecture, we're going to start talking about the working through and solving the hydrogen atom and hydrogen-like atoms. And uh, as in our other systems, we're going to approach this problem by starting with a diagram of the system. What are the particles and their characteristics, such as their position, charges, masses, so on. And then we'll carefully choose a coordinate system based on the symmetry and dimensionality of the system. Then we'll develop or find expressions for the forces or the potential energy of the system. And then for any particles in motion in the system, we need to describe their kinetic energy. And then that gives us all the pieces that we need that we can put together to form the Hamiltonian and the Schrodinger equation. And then we will solve the Schrodinger equation and then go on from there to look at some of the characteristics of the energy levels, of the wave functions, of various other observables, such as maybe momentum or angular momentum in the system. And another important aspect of the hydrogen atom is that this is the starting point for multi-electron atoms and for molecules. So it turns out we can use the hydrogen atom as a starting point, or it gives us a set of basis functions, and it gives us some other tools that we can use to try to develop sort of in a building up sort of reductionist paradigm, where we start with simple systems and then we extend them to look at more complex systems. And so that's where the hydrogen atom sort of fits into things. And of course, along the way, we'll have to develop some approximation methods that employ what we know from the hydrogen atom. Okay, so we have a system here where we have a nucleus charge plus Z. Now, for the case of hydrogen, it would be +1 in terms of in terms of multiples of an electron's charge. And then, of course, we have an electron with a charge of -1 or minus an electron. Of course, the charge of an electron, sometimes given by Q sub E, also sometimes, which is a little bit confusing, is given by E. And so you have to use context to tell whether or not E in a particular instance is units, and as well as context to determine whether or not E is the Euler's number, or whether it represents the charge of an electron. But it is 1.602 times 10 to the minus 19 coulombs. That's the SI unit of charge. So we have one electron, one nucleus. And again, in the case of a proton, it's going to have a charge of, for a hydrogen, it's going to be, the nucleus would just be a proton, and it would be, the charge would be plus E. But we can also generalize and look at other hydrogen-like atoms, other hydrogen-like atom ions, like we could look at, say, helium plus or lithium 2 plus, using essentially the same model by just adding the extension of making the charge be plus Z times E. where Z is the atomic number. And we have a coordinate system where essentially we have our nucleus and our electron, and there's the distance between them is r. We'll use little r. Previously we used big R to capital R to describe bonds, and so we're going to stick with that, and we'll use little r, lowercase r, to represent the distance in the hydrogen atom. Then our potential energy, V, which again represents the forces in the system, and it's given by minus Z E squared, where again Z is that atomic number, over 4 pi epsilon naught R. And again, E squared here is the charge of an electron squared, and R is the distance, and epsilon naught is the dielectric permittivity of free space. It's kind of like the free space's dielectric constant, and it is free space, sometimes called permittivity of vacuum. And it is given by epsilon naught equals 8.854 times 10 to the minus 12 Coulomb squared per Newton per square meter. And there's other ways to express it. That's one set of units that works. You can combine the newtons and meters in terms of joules, that sort of thing. So now implicitly here, I've switched to, I'm not considering the motion of the nucleus itself. We're going to assume that the nucleus itself is fixed, or essentially we're implicitly switching to relative coordinates with reduced mass, like we did previously with the harmonic oscillator and the rigid rotor. And so we're essentially talking about now whenever the electron moves, there's always going to be motion about some center of mass, but we're going to treat that as relatively fixed, or we're going to use these relative coordinates, center of mass coordinates, in which case we have a reduced mass mu, which is going to be equal to the mass of an electron times the mass of our nucleus over the mass of an electron plus the mass of a nucleus. But in the case of the proton, it's, of course, the mass of an electron is 9.11 times 10 to the minus 31 kilograms. Sorry, 9.1, yeah, 11 or 109, depending on how many significant figures you keep track of. And our mass of a proton, if we use that as our nucleus, is 1.66 times 10 to the minus 27 kilograms. So it's much, it's about almost 2,000 times heavier than an electron. And as we saw before, if we're talking about motion about a center of mass, and we switch to these kind of relative coordinates, the reduced mass is going to be almost the same as the mass of the lighter of the two bodies, so mass of the electron in this case. In other words, the electron is what's doing most of the moving in this system. That's going to be a little bit less than an electron. So often we use mass of an electron and mu interchangeably because they're about the same out to 3 or 4 sig figs. Okay, so then let's see what else to say about this. So this is let's look at this potential energy for a second. Let's go back to that. So we have the z e squared over 4 pi epsilon naught r. So this is a 1 over r type potential, and that's the nature of a Coulomb potential. It gets it drops to minus infinity at r equals 0. So this is a very deep potential well, and that's going to have some. The other thing is the way this is defined. We're essentially setting our energy 0 at the energy of an electron when the electron is placed at infinity with respect to the nucleus. So essentially the ionized molecule sort of at rest with minimal or no motion of the electron. That would be the 0 of energy. So most of the energy levels in the system are actually going to be they're going to be bound states where the electron is bound to the electron, so they're going to be lower in energy than 0. So we've implicitly set our energy 0 such that all of our energies are going to be negative. And again, that's relative to some 0. We're not breaking the laws of conservation of energy. So far, all of our we've usually set our 0 of energy at the molecule or the system at rest. In this case, it's defined a little bit differently, but we can't place our 0 at the minimum of the potential energy curve because the minimum of the potential energy curve is at minus infinity. So that's not convenient. All right. So then our Hamiltonian is going to be given by minus h bar squared over 2 times, we can go ahead and use the mass of an electron, del squared, this is our overall, this is our kinetic energy operator, and it's the electron essentially that's moving, and that del squared, that's the second derivative operator, plus v, which is a function of r. And because our system is essentially spherically symmetric, we have this central potential where the potential energy depends on the distance between the nucleus and the electron. So therefore, the natural set of coordinates, and really the only set that's practical, at least for initially trying to solve the Schrodinger equation, is spherical polar coordinates. And we previously discussed spherical polar coordinates, and I will not repeat them here. You could look at the previous discussion of spherical polar coordinates in the discussion of the rigid rotor. However, we do need to look at what del squared looks like in spherical polar coordinates, and we're going to have to treat it a little bit differently than we did in the rigid rotor case. First of all, we're using lowercase r instead of capital R. And so that's going to give us that del squared is equal to, the standard result is 1 over r squared d dr, r squared d dr, plus, so this is the radial term. Or radial part. And then we have our angular part. It still has r in it, but it has the derivatives with respect to the angles. So it doesn't have any derivatives with respect to the radial distance. So we have, and I say radial part, radial meaning, r, that's the radius. So we get 1 over r squared sine theta d theta sine theta d theta. That's the theta dependent part, and then we have 1 over r squared sine squared theta, or we could use parentheses around sine theta and square it. D squared d phi squared, where phi is the other of the two angles in spherical polar coordinates. And this we previously said was the Legendrian, or the angular part. And this has to do with the angular momentum of the electron sort of rotating around the atom, which there isn't always, but there can be some angular momentum associated with motion of the electron. And we know that the kinetic energy associated with angular momentum is given by L squared over 2I, where L, of course, that's our angular momentum operator. And since we already know what the angular momentum operator is in terms of these derivatives with respect to theta and phi, then we can rewrite our kinetic energy. First of all, we can pull out a factor of 2 times the mass of an electron times r squared, and that gives us minus h bar squared over 2 MER squared. So this MER squared, that is the moment of inertia. So that's the 2I part. And we have d dr r squared d dr. then we're going to need a minus sign because there's a minus out front here. L squared, and that's, yeah, we already have the 2i in the denominator there. So this somewhat simplifies our expression for the kinetic energy part of the Hamiltonian. We can represent L squared using, or we can represent the angular part using the L squared operator, which we had previously developed. And this hints at, if we have two different contributions to kinetic energy, there's sort of kinetic energy associated with motion, changes in R, so changes in the electron nuclear distance, and we have, so you can imagine the electron sort of bouncing back and forth between, but not orbiting, just sort of changing R, not changing theta and phi, and there would be that kind of motion, and then there would be the rotation motion that would be captured by the L squared operator. So then, since our kinetic energy is broken up this way, and our potential energy just depends on R, it doesn't depend on theta and phi, then it may be the case that, so based on the sort of principle of separation of variables, we can divide our Hamiltonian into sort of a radial part and an angular part, and therefore it makes sense that our wave function is going to be, of course, it's going to be a function of R, theta, and phi, and it's going to be some function of R and some other function that's going to be, we'll call it, for the moment, we're going to throw this away in just a minute, but g of theta and phi. So it's going to be a product of two functions. And because we already know what the solutions to the angular momentum, the rigid rotor type Hamiltonian, look like, and we're going to make an assumption that our functions are of this form. We're going to have this big R sub NL. That's going to be our radial function of R. And then the other function is going to be the function that we've used previously, these spherical harmonics, which are functions of theta and phi. So we're going to start off just sort of assuming that it might be of this form, and then we'll see that it works. And again, this is suggested by separation of variables, the principle of separation of variables, which again, it's not a universal principle, but it's telling you that you might be able to factor your solution into a product of simpler functions, and that this could help you to solve the differential equation. So this is just kind of a strategy for solving partial differential equations in this case. And again, these YLMs are the Legendre polynomials or the spherical harmonics. And we've seen what a few of those look like. It's some function of theta involving sines and cosines, and then there's a factor of a complex exponential e to the I m phi. And so then we can use, if we make this assumption, then we can do a little bit more simplifying of our Schrodinger equation, because we're going to have h psi equals e psi, and the h is going to have this L squared term, and we already know that L squared acting on y Lm is h bar squared L plus 1 y Lm, and therefore if this is true of the spherical harmonic, and the wave function psi is a product of some radial part that has no angular dependence and a spherical harmonic, then this would also be true for L squared acting on psi would also be h bar squared L times L plus 1 psi. And again, this is sort of the utility of these separation of variables concept, is that we can use it to simplify these differential equations. Okay, so then the angular part in our Hamiltonian looks like L squared over 2I, and we can replace that with h bar squared L plus 1 over 2 mu r squared. So then combining this, putting this all together, we end up with this Schrodinger equation that looks as follows. First of all, we've essentially been able to implicitly remove the angular dependence. We can always put it back in later, but for the sake of determining the radial part, we're going to assume that we know what the angular part is, and then plug in eigenvalues for the operator. And this allows us to simplify our Schrodinger equation a little bit. So the Schrodinger equation for the radial part is going to be minus h bar squared over 2 mu 1 over r squared ddr. Since now we have essentially a one-dimensional Hamiltonian, we're going to switch from using partial derivatives to using regular derivatives. So then we have r squared ddr, and then this is acting on our RNL function, which we don't, that's what we're trying to find here. Then we have plus, we're going to have all of these other stuff, the angular momentum part, h bar squared L times L plus 1 over 2 mu r squared minus ze squared over 4 pi epsilon naught r. So let's see, the h bar squared L times L plus 1 part, that's the kinetic energy. It represents the kinetic energy due to rotation. But we've kind of grouped it in here with the Coulomb term, this minus ze squared over 4 pi epsilon naught r. because it doesn't have any derivatives in it, so we might as well. And it has 1 over, well, it has 1 over r squared. So yeah, so it seems like this is where we should place it. And again, and we factored that out. That's multiplying all of that times r and l. That's going to be equal to our energy level times r and l. Now, why did I call it r and l and not just r? It's because, well, we're sort of, there's a little bit of maybe foreshadowing there, in that it turns out that the functional form of r depends on the two things: principal quantum number n, which we can sort of infer that there is some quantum number because all of our other systems so far have had some quantum number. So that's not a major assumption. And anyways, so we're just provisionally assuming it anyway. And that it also might depend on the L quantum number of angular momentum. And it turns out the energy level depends on the quantum number n. So this is sometimes called the centrifugal potential, in that it kind of looks like a potential. Right? We have a Coulomb potential here. It has 1 over r dependence. This has a 1 over r squared dependence. So it seems like it acts like a potential, and we can think about it as the energy associated with, if you have something spinning and you try to reduce r, like a skater trying to, like an ice skater in a spin, and they bring their arms in. It requires some work. It requires some energy to bring your arms in. You're sort of overcoming that centrifugal force. And of course, I know, strictly speaking, physics teachers like to drum it into you that there's no such thing as centrifugal force, but it's a useful fiction, and in some circumstances it's useful to refer to something as due to some centrifugal type effect, and so that the energy associated with that rotation, we can refer to it using this centrifugal potential. And whether or not you are comfortable with that designation, that's just sort of what it's called, and maybe we just shouldn't worry too much about it, and move on. So now it does pop up, though, in that it acts like a repulsive potential. It's pushing an electron away from the nucleus. So if we have an electron that has angular momentum, this centrifugal potential is going to push that electron away from the nucleus, right? It's going to be repulsive as at short r, right? And in fact, as r goes to 0, this centrifugal potential is going to go to infinity, assuming that we have some non-zero angular momentum L, or angular momentum quantum number little l. So if little l equals 0, then centrifugal potential vanishes. We don't have to worry about it. But we can think of I like to talk about sort of countervailing forces, in that if we have a Coulomb potential, which we haven't really sketched yet, so let's go ahead and sketch it. If we have our Coulomb potential, it's a 1 over r potential. It's going to look like this. We're going to have energy going up along this y-axis, and we have r along the what is that? The abscissa along what's typically the x-axis, and we have this v equals minus e squared over 4 pi epsilon naught r, or minus z e squared if this is hydrogen-like. And then we have this 1 over r squared potential. So it's going to drop off more quickly because it's a 1 over r squared. So it's going to fall off more quickly than the 1 over r potential. It's going to get flat sooner. And at a shorter distance. And let's see what else to say about that. So that's the that's our centrifugal potential, which is this thing. So if we add them together, we end up with this kind of net potential that looks a little bit like that. And so we can see that, yeah, in some cases it looks like there's a little bit of, you may be able to support states in this sort of potential well. Yeah, there's a place for the electron to sit, but not necessarily. Because for different values of L, of course, this for higher values of L, this centrifugal term gets, relatively speaking, in an absolute value sort of sense, larger, and it could swamp out V at some for a fairly large range of. So there may be cases where our centrifugal potential doesn't allow certain states to exist. And for instance, that's why we can't have a 1p state. You can't put one quantum of angular momentum you can't the p states correspond to L equals 1, and there would be the centrifugal potential in that case at such a small r associated with the n equals 1 state, right? It has associated with a small radius. These are small states in terms of their radial size. And at that small radius, the centrifugal potential would be have too large a value, would swamp out the Coulomb potential. However, for n equals 2, the typical distance is r of r is longer, and you can have a 2p state. And you can think of this as being the fact that there isn't a 1p state as being related to the fact that there's this centrifugal potential. Okay. So let's move on to our solutions. First of all, let's just talk about the energy levels. So we'll talk about what the radial wave functions look like in a second, but right, there are two types of solutions. So I think we can agree, going back and looking at this Schrodinger equation, it's certainly more complicated than a lot of these other ones we've looked at so far. Well, maybe not more complicated than the, no, yeah, it's more complicated than the Ridge-Rotor as well, although, well, it depends on your perspective. But it turns out there is a solution to this. You can come up with a function that, when you put all this together, when you take the function, take the derivative of it, multiply it by r squared, then take the derivative again, then multiply by 1 over r squared, that you end up with something that cancels the centrifugal potential and the Coulomb potential, and so therefore ends up being an eigenfunction of the Hamiltonian. So it turns out some of the solutions are very simple, and they form a series, a polynomial series. Anyway, so and we'll see what those functions are in a minute, but right now let's look at the energy levels. So it turns out the energy level depends on the principal quantum number n, and you end up with this kind of messy looking set of constants. mass of an electron times the charge of an electron to the 4th power times z squared, where z is the atomic number of the nucleus. Then we have 2 and 4 pi epsilon naught squared h bar squared n squared. Now, of course, most of these things are just physical constants, so they all just kind of, they can all be grouped together to form a single constant. The important thing is this n squared in the denominator. In fact, we can take all of these constants and call them something called Rydberg. And Rydberg has units of energy. And our quantum number starts at 1 in this case. Oops. So we end up with a series of energy levels minus Rydberg over n squared. And by the way, the Rydberg constant is about 2.18 times 10 to the minus 18 joules, or one of the things that shows up in things like photoelectron spectroscopy is something called electron volts, and it's the energy of a single electron that is accelerated through a potential of 1 volt, through an electrostatic potential of 1 volt, and that's electron volt. And so that's again a fairly commonly used energy unit in atomic physics and in spectroscopy, and also in things like solid state physics. And a photon that has an energy of 1 eV has a wavelength of about 1240 nanometers. Which is in the near infrared. So we end up with a series of, and we'll look at these energy levels, sort of the spectrum of energy levels, or the energy level diagram shortly. The RNL are called the Laguerre polynomials. They're a set of functions involving an exponential function of R times some polynomial in R. And we'll see what those look like later. So let's consider for a moment, instead of plotting sort of the typical energy level diagram, well, we can do that. Typical energy level diagram, we plot it a little bit differently in that we're going to have any energy equals 0, and then we're going to have this, maybe our first energy level is going to be at minus a Rydberg, and that corresponds to n equals 1. And then for n equals 2, it's going to be minus Rydberg over 4. So it's going to be roughly up here. And then the next one is going to be minus Rydberg over 9. So I think roughly up here somewhere. So we have this set of states, and then of course, yeah, the next one's going to be, they're going to be sort of converging on, you end up with a series of energy levels converging on equals 0, right? If you put in n equals infinity, you're going to get energy is 0. So instead of having an evenly spaced ladder of states, or a ladder where the spacing, so let's see, so for the case of particle in a box, the spacing between rungs in the ladder gets bigger as the quantum number goes up. In the case of the harmonic oscillator, you have this evenly spaced ladder. In this case, we have the rungs getting smaller as the spacing between the rungs getting smaller as the quantum number goes up. And we'll talk more later about atomic spectroscopy, transitions between these various energy levels. However, before we plot the wave functions, let's look at our classical turning point, and maybe that'll give us some idea of what our wave functions will look like. So you may recall, in order to find our classical turning point, we essentially plot our quantum mechanical energy levels, which are a series of discrete energy levels that we can represent with horizontal lines in our energy diagram. And then we can plot that on together with, make a combined plot of that and the potential energy. And then where the energy levels meet the potential energy, that'll give us what our classical turning points are. The classical turning point is the point where the energy of the system is equal to the potential energy system. And so there, if it were a classical system, that's where the particle sort of stops and turns around. So again, if we plot energy increasing, so that we have plot a potential curve, and then we have minus the Rydberg. So if we have n equals 1 and n equals 2, so on, have our n equals 3 up there. So it's clear that as we go to higher and higher quantum numbers, the classical turning point moves further and further out. And we can actually come up with an expression that tells us where these turning points exist, where they occur as a function of quantum number. So if we do that, we're going to get, we have to set energy is equal to potential energy, where energy is a function of the quantum number n. We're going to get minus, we're going to go back to, instead of using the Rydberg, we're going to go back to all of our constants because some of them cancel. Minus me e to the fourth z squared. Might as well keep the z in there. We could set z equals 1 to make a slightly simpler expression. Oops. So that's our energy levels, and it's negative, and then this is also negative, minus z e squared over 4 pi epsilon naught r. And of course, it's not just r, this is r at the classical turning point, right? Because we expect these two quantities to be equal at the classical turning point. So we're going to substitute rctp. We're going to plug that in for r. And then essentially the problem is to solve for r. And you see that some things cancel, right? You get a factor of z that cancels from both sides. You get a factor of e squared that cancels from both sides. You get one of those 4 pi epsilon naughts cancels out. And you end up with, but you know, the h bar squareds sort of stick around. And so you end up with that the classical turning point is 2 h bar squared 4 pi epsilon naught over me e squared times, and here's where, so I put all the physical constants out front, then I put the things that depend on our system next, and it's going to be n squared over z, where z is the atomic number of the nucleus. So the classical turning point depends on the quantum number squared. It's going to, so if you end up with, and you can put numbers in here for n equals 1, we get that the classical turning point is at 52.9 picometers, or 0.529 angstroms. And this is nice in that it turns out this ends up being the n equals 1 classical turning point ends up being something called the Bohr radius. Oh, and sorry, this is yeah, we call it A aught equals the Bohr radius. And this gives us a sort of fundamental length scale or fundamental, yardstick for the size of atoms, as we'll see. And I think that is enough for this lecture. Next lecture, we'll talk a little bit about atomic spectra in the next video, and we'll also look at what these radial functions, what these RNLs look like, sort of what the shape of the orbitals are for the hydrogen atom.